This is lesson 9, related rates word problems. Related rates problems have everything to do with time. You can read my little blurbs here, but most importantly for us is that calculus in general is the study of change, right? Derivatives are rates of change. And as humans, we often experience change thanks to our perception of time, right? As time passes, things change, right? It all ties back into observing, the stars and the moon and all that and whatnot. So time and calculus go hand in hand. Let's move on down to the next page here. Like we said, derivative is a rate of change. We measure how an object or quantity changes over the course of time. We might even have a function that describes a quantity in terms of time. This first example is not a actual related rates problems in its standard sense. This is actually a simpler example where we do have a function described in terms of time. The position of this alien spacecraft S is given by the S of t function. We want to find ds dt. Since we already see t representing time in the function, this is pretty straightforward. It's the same type of derivative stuff we've been doing, except instead of y and x, we see s and then t. So we do have to stick with proper variables and notation. Ds dt simplifies after chain rule into 2 over t. Units would be meters per second. Once we have the rate of change of this position, we can plug in numbers like t equals 2 to find a rate of change at a certain time. Explain the meaning and context. Be prepared to do this. It's fairly common in AP prompts. Here we would say at a time of 2 seconds, the spacecraft is moving on the horizon at 1 meter per second. So much of the change in the universe that we observe can be measured in terms of time, but that doesn't mean that we always have a function that directly links our quantity to time. Okay. For example, imagine a spherical balloon, hypothetical, that's being filled up with helium gas. As time passes, volume is changing, but we don't necessarily have the equation for that change. We might have an equation for volume of a sphere, and we can still attempt to differentiate it with respect to time, even though I don't see time directly showing up in that equation. All right. We do see volume and radius. Both of those quantities are changing as the balloon fills up. So we are essentially differentiating this equation implicitly with respect to time. Derivative of velocity, we would just call it dv dt. The 4/3 pi just carries down. This r cubed becomes 3r squared. So when you simplify, we've got the 4 pi r squared. Then we also have to multiply in dr dt because of the implicit nature of this. There might be some relation of radius to time. We just don't know what it is. So the best we can say when differentiating r is dr dt. How do you know when you have a related rates problem? Well, there will be several rates of change working in relation to each other. Often there's more than 2 variables. Problems examine how quantities change over time. You'll have information given about rates of change with respect to time. Okay, sometimes you have to introduce the actual t variable to represent time because it's not in the original equation. And it usually ends up with determining an equation that relates the quantities that you do have, differentiate with respect to t. Here are my recommended steps. Number 1, I say we should draw a picture. I'll admit there are some setups where this might not be necessary, but there are many where it does help quite a bit to help see the relationship, especially when we have geometric setups. We draw a picture, assign variables to the quantities we're using. We don't want to assign a number directly to a quantity unless it's a constant and never changes. All right, write your equation that relates these changing variables. Okay, again, don't include specific numbers unless they're constant. Then we differentiate implicitly using t for time. Then after you're done with the differentiation, done with the calculus stuff, only then can you start subbing in specific values for your different variables that might be referenced in the problem. Let's look at the first example. We return to the balloon, spherical balloon, filling with gas. There's a moment at which the radius is 2 feet, but again, the radius is changing throughout this exercise, but there will be eventually a moment where the radius is 2. And at that moment, the radius happens to be increasing at the rate of 1/6 of a foot per minute. At that same time, how fast is volume changing? We see clues that time are involved. I see the word time. I see a rate of change given in feet per minute, which is a unit of time, right? So our first goal upon seeing those clues is to set up an equation for a related rates problem. We're being asked about volume, so most likely that's the equation we want to set up. And this, of course, comes from geometry class, volume of a sphere, 4/3 pi r cubed, right? In fact, I'm using just the same derivative that we saw in the example on the previous page, implicit differentiation of v and r with respect to t. Okay, so I haven't even addressed the 2 or the 1/6. That has to happen after the differentiation. Now that I've got it, I can start plugging in the specifics relating to this certain moment in time. So here I plug in my radius of 2. dr dt, rate of change of the radius, is the 1/6. Then I can simplify, make sure you get the right units. We found how fast volume is changing. That's going to be a cubic foot change per minute. All right, so throughout the rest of this lesson, we're just going to see a variety of examples. Every related rates problem is different. I can't say to you, hey, there's 3 specific types that you can just memorize. Every problem's different. What's most important is you recognize when you're dealing with related rates, and you can adequately draw a picture, come up with a formula that you can differentiate. That being said, a lot of these setups are somewhat common. The classic person next to a light pole setup. We've got a 6-foot tall person indicated here in my sketch. 20-foot tall street light right here. And the person's walking away at 7 feet per second. At what rate is the length of the shadow increasing? In my picture, you can imagine the hypotenuse is the light streaming down from the street light. Shadows, of course, live on the ground. So it's this X segment that would represent the actual shadow. Y is not something we're directly asked for, but it is going to be important. And that's, of course, going to be the distance from the street light to our individual. I also noted that the ratios that I'm going to be setting up here involve tangent, but you don't actually need to know this angle. You don't need to use trig here. You do use similar triangles from geometry. We know the ratio of 6, which is constant, to this x, which is changing, is the same as the ratio of 20 to y plus x. As this person moves away from the street light, the shadow is going to change size. The distance y is going to change size, but this ratio will always hold up. And that's the equation we're going to work with and eventually differentiate. I personally don't want to differentiate it in this form. That looks yucky. I don't want to deal with quotient rule if I don't have to. I suspect we can simplify. So here's me doing some algebra manipulation. And what do you know? It comes out actually really, really nice. This is very, very friendly to work with. But we want rate of change with respect to time, right? The clue here would have been units of feet per second. Second is come into the mix, well, time is involved. So again, we differentiate both sides with respect to time. Y becomes dy dt. X becomes dx dt. Okay. Now that I'm done with that, we can plug in given information in the hopes that we can solve for whatever we want. We want to find the rate the shadow is increasing, shadow being x, that would be dx dt is the rate of change of x. Luckily for us, this other unknown dy dt precisely lines up with the given information. That's the rate that we're moving away from the street light. So I plug my 7 in over here, simple algebra. There's your answer, and units would be feet per second. All right, 9.4. 9.4. Water-filled tank. This is another common problem. Cones tend to show up fairly frequently. I don't know how probable it is to have a cone-shaped water-filled tank. That seems like a recipe for disaster, but that's not our concern right now. We've got a 20-foot tall cone, talking about the vertical height, circular base on top, radius of 5. I'm indicating that all in this tiny picture over here. Pictures really do help. Water is running out of the bottom of the tank at a constant rate. That's a number we can make use of. Cubic feet per minute tells us a couple things. It helps us establish that this is definitely a rate of change of a volume. It's also with respect to time, so that's the clue that this was a related rates problem. We want to know how fast is the water level falling. So the H that I've drawn in this picture here, it's hard to see, but that H represents height of the water. It's decreasing. So it looks like we're going to be interested in dH dt. And we might start with the formula that relates volumes and heights and radii of a cone right here from geometry. But I write it down and immediately I don't love it because this just has a few too many variables from a differentiation standpoint. Okay, it could be done, but it'll end up being complicated. It's likely to make silly mistakes. It would be a lot better if instead of R and H, we could somehow just have one variable on that side. And as you can see, looking at my work, there is a way to do that. All right, so I've got this secondary equation that I'm working on over to the side here. Just noticing the fact that even as the water level is changing, there's like a cone within a cone. We've got the unchanging cone that represents the entire tank, but there's the cone of water that's getting smaller as water drips out, but it does retain the same shape as the original cone, albeit smaller. So we've got two similar triangles again here. And we can say that the ratio of radius 5 to height 20 is going to equal the ratio of radius of just the water, I'm calling that R, to H, which is the height of just the water portion. So R over H always equals 5 over 20. We can solve that to see that R is always equal to H over 4. And then we can just get rid of R entirely. We can replace R with H over 4. Now, you might be wondering, does it matter if I get rid of the R or get rid of the H? Usually, yes, it does. As far as which one you want to keep around, look again at the given information. We're interested in the water level that corresponds to the height. We need to keep height around to solve this problem. We don't need R. So that's how I decided to solve this for R and get rid of R. Okay, so here's me rewriting our volume. I haven't done any calculus yet. I'm just doing the substitution and cleaning this thing up a little bit. And then I go down to the implicit differentiation step using V as the left side. This other expression is my right side. So dV dt equals constant times 3h squared times dH dt. I've condensed all my constants to a easier to read value. And now we think about plugging in given information. Be really careful here. We have a rate of change of volume that seems to correspond with a dV dt, but volume is getting smaller. Water is leaking out of the tank. So you as the problem solver have to know to plug in not the actual 2 that you see here, but a negative 2. It's a really common mistake that people might make is forgetting that negative. Okay. At the same time, we know the height of the water is 8. So we're plugging that in for H. There's only one more unknown, and it's exactly the thing we're trying to find. So at this point, it's algebra, blah, 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 blah. We end up over here. Don't forget your units of feet per minute. On to the last page. There's a lot going on here. Two different setups, but three different parts for each one. And because I didn't have much space, I didn't actually draw a picture for 9.5. It still could be helpful, but we'll do without for now. Length of a rectangle is decreasing while the width is increasing. And we're going to be interested in the precise moment when L happens to be 12, W is 5. So firstly, rate of change of area. That means we probably want to start with an equation for area of a rectangle. I went with A equals L times W. I do have a lot of variables here, but unlike the previous problem, we don't have a nice, easy way to necessarily eliminate one of them. But this derivative isn't too bad. Derivative of A is dA dt. Derivative of L times W plus derivative of W times L. I'm using product rule there. And dA dt, that's what we want to find. Everything else here we can plug in. Rate of change of length, make sure you make it a -2. Width at this moment is 5, length is 12, dW dt, +2. Units have to be centimeters squared per second. How is the perimeter changing at that same moment? Start with your equation for perimeter in terms of L and W. Implicit differentiation of every term with respect to t, plugging in the same given information for the most part. We get an answer of 0. I forgot to put units on this one, but it would be centimeters per second. Length of diagonal, this is the part where you might have been most helped with the picture. Draw it out on your own if you like, but basically the length, width, and diagonal of this rectangle are making a right triangle, and it's a special right triangle. 5, 12, and hopefully you remember 13. But I'm getting ahead of myself. Before we worry about plugging in numbers like that, we want to take what's essentially the Pythagorean theorem here. Hypotenuse squared equals side squared plus side squared. Differentiate everywhere with respect to t. And then we start plugging in. We knew what L and dL dt were. Same for the W's. D was not given, but again, special right triangle, we know it's going to be 13 at this moment. The only unknown left is the thing we are trying to figure out, the rate of change of the length of the diagonal in centimeters per second. All right, final problem. Another common setup, ladder against a house, and it starts to slide away. Ladder is always 10 feet, that doesn't change. I've drawn my picture here. What does change is the position of the top and base of the ladder, which correspond to then the height and base of this triangle. So H and B are changing. The angle here is changing. We might actually need that in this problem. The 10 is constant, right? We want to find the rate of change, firstly, for the height of the top of the ladder. Basically, the rate of change of H, dH, dt. So we want to start with an equation that relates these variables. And the easiest one to go for, again, is Pythagorean theorem. B squared plus H squared has to equal 10 squared. Differentiate every part of that. Even the right side, being a constant, goes to 0. Then we start plugging things in. Okay. Base is moving away at 8 feet per second. So the base is getting longer, hence +8 here. This is the moment when the base was 6. The height, did it tell us? Oh, okay, it didn't directly tell us the height, but again, special triangle or Pythagorean theorem, it must have been 8, 6, 8, 10 triangle. All right, so we plug that in as well. And again, the only thing left, the only unknown left is what we're trying to solve for. So then we go to algebra to get an answer that comes out to be negative, which makes sense because the height should be getting smaller. It should have a negative rate of change. area of the triangle formed by ladder, wall, and I said rectangle here. I guess what I meant was the ground. Start with a formula for area. Go with 1/2 base times height. Okay. Implicit differentiation everywhere. We're plugging in a lot of the same information, including the -6. That was our answer in part A. Rate of change of area ends up as 14 centimeters squared per second. And finally, this one's a little trickier. It's going to involve some trig. The angle here we said is changing. So we need some kind of equation that relates this angle now to our h and our b. And of course, we're going to bring in a trig function, opposite, adjacent, or y over x. We know here tangent equals the h over b. Don't be afraid here. It's still the same derivative rules. You guys mastered them. You aced the quiz. So tangent theta becomes secant squared theta, just multiply in d theta dt. H over b, you can see, I'm going with quotient rule here. All right. The rest is algebra, but there's some little triggy stuff here. Okay. All these things in the numerator are from previous parts of the problem, but what do I plug in for? We actually never know exactly what to plug in for theta, and we don't have to, because instead I'm just going to plug in for secant theta, right? At the moment when the base was 6, hypotenuse is 10, h was 8, we can make a secant ratio out of that. Secant is the reciprocal of cosine. Cosine was always going to be adjacent over hypotenuse. So essentially at this moment, cosine is 6 over 10. Therefore, secant is 10 over 6. So what I'm doing, transitioning steps here, I'm dividing the secant squared to the bottom of the right side and immediately replacing it with 10 over 6 squared. And you've got some manipulation that actually works out really, really nice. The units on that angle, in this course, we always are dealing with radians unless specifically told not to. So that would be interpreted as -1 radians of change per second. All right, hope that helped with related rates review. Thanks for watching. Let me know what questions you might have.